All right, before we get started, let's just quickly go over our plans for the final exam. So here's a general, tentative plan. The final exam itself, it's going to be comprehensive, like what we discussed in the course syllabus. So basically, it covers everything we discussed this quarter. So that includes all the materials of midterm 1 and 2, so that's chapter 1 all the way to mid of chapter 5, and everything we will discuss in after midterm 2 all the way into our Wednesday's class, right? So my plan is for the final exam to cover chapters 1 all the way to chapter 6, and maybe the one component phase diagram. I'll see how that goes on our Wednesday's lecture, but that's a tentative plan. The take-home message is basically whatever we covered all the way until Wednesday, that's going to be our final exam coverage. Our Friday is going to be a review section of the entire quarter. When and where, this part I really don't have any control on. It's set by your registration office. Basically, I also follow the instruction of the registration office. So you're in my lecture 1, which is your final exam will take place on next Monday, 11:30 to 2:30 in this room. And what to expect in the final, likewise, your final exam is also going to be open book, open note, anything printed out is fine, textbook is fine, no electronic devices. And the structure of your final exam is basically double the length of the midterm exam, but you got triple the time. Your final exam is 3 hours. So specifically, you will expect 20 true and false problems, 10 short answer problems, and then 2 comprehensive problems. Same style as your midterm exams, but this time you got double the length, triple the time. And we also have 10 extra credit left. I think at the beginning of the lecture, I was saying this class we have 30 extra credit. So now we still have 10 extra credit left after all the survey and everything. So whatever left for the extra credit, I'll post it in our final exam. Let's see, what to expect after the final exam. Okay, so after the final exam, everything pretty standard. Your TA and I are very fast graders, so I'll try to grade your final as soon as possible. The only thing that's different is we do not take regrade requests for final exam. We grade it on paper, so you'll see a grade there. And if you want to see the exam, like the physical copy of the exam, you need to contact us directly. We also don't post any answer keys or walkthrough for the final exam. Just because it's an evaluation at the end of the quarter. Final note for discussion worksheet. So you have one more discussion worksheet, which is worksheet number 8. So that discussion worksheet will be due this Friday. All right, so that's a little bit different. The whole point here of making that worksheet due earlier is so that we can post the answer key and people can use that worksheet to study for the final exam. So that's why we put the final exam to be due prior on this Friday, prior to your final exam. I also think your TA made your discussion worksheet number 8 a little bit shorter, meaning like you have less graded by accuracy problem. So the whole point here is we still want you to have that discussion worksheet number 8, especially when we're talking about chapter 5 on reaction equilibrium. And also we want to give you enough time to study, to use it to study for the final exam. So the due date of the discussion worksheet 8 is this Friday. Just keep in mind, it's different from your previous worksheets. Study suggestions, everything pretty much stays the same, right? You have discussion worksheet, chapter end problems. I mean, by now you should know our style of the midterm exam. I don't want to surprise you, right? So if you study well using the material we discussed, you shouldn't be surprised during the exam. And one more thing that I added there is I highly recommend you practice your final exam with a timer on. So when I say with a timer on, it's not necessarily mean you create your final exam. It's more like, hey, how much time do I need to answer a true and false problem, right? Like so that you can allocate your time accordingly and you're not running out of time at the end. And one last administrative note. So the course evaluation for this quarter is open on your My UCLA account. So please log in and finish that survey by June 8th. We won't be able to see your survey result until we submit your final grade. So it's like a double-blind real evaluation. So do go and finish that evaluation. I have also posted like an extra credit item. So once you finish doing the final evaluation, click on the link and say yes, and to get that full extra credit. Okay, so that's all the plans for the final exam. I'll have more information on Friday, since right now I don't know how much I'm going to cover. But that's our tentative plan for now. Any questions? Nope? Okay, awesome. All right, so back to thermodynamics. In our last lecture, we end up talking about so in our previous lectures, right, we start by talking about what is reaction equilibrium, what is the relationship of ideal gas reaction equilibrium, especially we defined the equilibrium constant. And then at the end of our last lecture, we spent time talking about what is the temperature dependence of equilibrium constant. Or the other way to put it is we derived the Van 't Hoff's equation to get the relationship of the change of your equilibrium constant, d ln k naught over dt, and that equals to delta H naught over RT squared. So the full derivation is in the annotated notes or in our lecture walkthrough. So how exactly do we use it, and what does it mean? So let's look at one example problem together. We'll see this example very often. So the reaction of interest here is N2 gas reacting with hydrogen gas goes to ammonia. So ammonia production is one of the most important chemical reactions in modern civilization, right? It produces ammonia and then the fertile that we use for agriculture. So the plot here gives us a plot of ln Kp over 1 over T. So the y-axis is ln Kp naught, and the x-axis is 1 over T. Or in our previous derivation, we know that the slope of this plot, or d ln Kp naught, divided by d 1 over T equals to negative delta H naught over R. Right, so this is the variation of the Van 't Hoff's equation using basic calculus. And we also discussed that in our last lecture. Now, what that means is in this equation, right, the question asks us to estimate delta H naught for this reaction, given the plot. So effectively, what the question is asking us to do, we have a line, we have a straight linear relationship between your ln Kp naught and 1 over T. Right, so the question is asking us to use the plot to find what is the slope of this curve, ln Kp naught versus 1 over T. And that slope of the curve is our negative delta H naught over R. Or this one is our slope. Right, so by solving for the slope times negative R, we can get our delta H naught. All right, so how do we do that? So if we think about it, let's take one point like here, right? That's where my, say, ln Kp naught equals to 0. And my T minus 1 is roughly equals to 0.0022. It's an estimate, right? We know that this is 0.002 and that this is about 0.0022. It doesn't need to be exact, it's an estimate. Or similarly, let's put this one to be around like 0.2. I'm gonna pick a random point on there so that my 1 over T is about 0.0040. And on the left-hand side, let's see what that is. Like my ln Kp naught is about 20. Right, so we can estimate the slope using these 2 points. You can pick any 2 points on this linear curve. You're bound to get similar results. So our slope equals to delta y over delta x. So 20 minus 0 over 0.0040 minus 0.0022. And we estimate our slope to be about 1.11 times 10 to the 4. And the unit here is Kelvin. You want to know why the unit here is Kelvin? Right, so ln Kp doesn't have any unit. Our x-axis has a unit of K minus 1, so the slope must have the unit of Kelvin. And then from there, we can use our slope times negative R equals to delta H naught to solve for delta H naught of the reaction. Right, so note that this question said it's solving for delta H naught for the range of 300 to 500 K. So that's about this area. Because delta H naught itself is a function of temperature. It's just when the temperature change is small, we can neglect the dependence of delta H versus temperature. Right, so you can solve for a numeric answer, and in this case, we can solve delta H naught to be negative 92.4 kilojoule per mole. All right. So from here, I want to spend a little bit more time on this equation here, which is our ammonia formation reaction. So the way to put it is we're going to go over one of the plots that's shown in your textbook and try to get an idea. Let me just make some space here. So the goal here is of considering this example that N2 gas plus 3H2 goes to 2 NH3 gas. And we just solved that delta H naught in the range of 300 to 500 K is around negative 92.4 kilojoule per mole. We can also give you that my Cp naught is a constant. And now the question is, can you plot the following things with respect to temperature? Or can you predict how these things are going to change with temperature? So these are my R ln Kp naught, delta G naught, delta H naught, and delta S naught. So these are the few things that related to equilibrium, reaction equilibrium that we care about, right? So how does these terms, equilibrium constant and my thermodynamic state functions, how do they change with respect to temperature? All right, so by understanding this plot, we'll be able to have an idea to how to use thermodynamics to predict the shift of equilibrium that we will discuss subsequently. All right, so the goal here is to plot the change of my state functions versus temperature. And this plot is in your textbook, so if you're not in the room watching the recording, you can check with the textbook to get an idea about what that looks like. So the whole point is we want to plot a few things with respect to temperature. All right, so what are the things we know in here? Like, where should we start? The first thing we should start is thinking about what do we know about how these state functions change with respect to temperature. Right? So one of the things we discussed is the delta H's dependence on temperature, or the delta H of the reaction is basically this integral delta Cp naught dt. Right, so that's how my delta H, the reaction enthalpy, change with respect to temperature. It's related to the molar isobaric heat capacity. Now, in this question, we're giving you, first of all, the heat capacity itself is a constant. And now we know this reaction is an exothermic reaction. It releases heat. So we're looking at pretty much a linear relationship for my delta H. So we can think about it starts here. I didn't put anything on the y-axis because your delta H, delta S, delta G, and ln Kp have different dimensionalities. But we'll start somewhere here. And it's going to be basically a linear curve. It's an estimate, right? So some constant plus some constant over P. Now this A is basically what your Cp naught is, which is a constant. And the C tells you what is your delta H, assuming our temperature is approaching 0 Kelvin. So that's delta H. All right. What about delta S? So we know delta S. We know two different things of this reaction. First thing is delta S approaches 0 when temperature approaches 0. So if we're thinking about delta S, that's where we're going to start from. Right? Delta S equals to 0 when temperature is 0. Secondly, for this reaction, how does my reaction entropy change? It's an ideal gas phase reaction, so you count the number of gases converted on the left and right-hand side. So in this reaction, we see that on the left-hand side, we have 4 moles of gas. On the right-hand side, we only have 2 moles of gas. So my delta S will decrease as the reaction proceeds. All right, because we're decreasing the amount of gas. So the way to put it is we're expecting some kind of plot that goes down. All right, so the two things we write down. Delta S is 0 when temperature is 0. Delta S is a negative number when my temperature proceeds. So taking these two together, we can obviously make some conclusions about my delta G. So my delta G naught equals to delta H naught minus T delta S naught. Right, so when delta G at 0 K, my delta G naught equals to my delta H naught. Because when temperature approaches 0 Kelvin, my delta S is effectively 0, and that T delta S term becomes 0. Right, so the delta G and delta H must have the same starting point. And then when temperature increases, right, so we have a negative in front of my delta S. Right, so my delta G naught equals to delta H naught minus T delta S. So we effectively have increase of my delta G while my temperature increases. All right. And what about my R ln Kp? Right, so if you think about the R ln Kp term, what do we have? We have delta G naught equals to negative RT ln Kp. So because of that negative sign in front of my negative RT ln Kp, so when my delta G go up, my ln Kp must come down. And the other thing to think about it is since my delta G naught equals to negative RT ln Kp, so when my delta G naught equals to 0, so we cross that 0 at the x-axis. When my delta G naught equals to 0, my ln Kp naught must also equal to 0. And also, what else do we know? We know that when delta G naught increase, my ln Kp naught would decrease because of the negative sign. So what that gives us is a decrease. All right, and if you think about what does it mean? What does each point here mean? So if we look at this point here, when that equals to 0, what do we have? We have ln Kp equals to 0 at that point. And what does ln Kp equals to 0 mean for this specific reaction? Now, if you write down the definition of ln Kp, and in here, at this point, we can conclude that, well, ln Kp naught equals to 0, so my Kp naught must equal to 1. And if we write down the Kp naught, the definition of my Kp naught, well, for this reaction, we have product. We have the pressure of NH3 squared divided by P naught squared times the pressure of N2 divided by P naught times pressure of H3 divided by P naught to the third. And this must equal to 1. All right, so we have some information regarding how does the ratio of my reactant and product would shift with respect to temperature by simply looking at the figure. So obviously, we can take one more step to see, like, what if we go to the temperature that's below this temperature, right? So what does that mean? So in here, we have our ln Kp naught to be positive, right? So my Kp naught itself is going to be larger than 1 number, so this ratio will be larger than 1. So you can expect what's the percentage of your NH3 versus N2 and H2 at different temperature. So this is taking one step further to see, like, qualitatively, when we're talking about reaction equilibrium, again, in thermodynamics, we're using thermodynamics as a tool to give us relationship between things we can measure and also between things that we can derive. And one more thing, now look at it. We have our ln Kp here, right? We see that decreases when temperature increase. We can get to the same conclusion by using our Van 't Hoff's equation, right? So what is our Van 't Hoff's equation? So our Van 't Hoff's equation gives us the d ln Kp over dt equals to negative delta H naught over RT squared. So that's our Van 't Hoff's equation. All right. So what does it mean? Wait. No negative when we're looking at that real one. So what does that mean? So my delta H is negative. So a negative delta H tells me when my Kp naught when my temperature increases, my Kp naught must decrease. All right, so from the Van 't Hoff's equation, delta H is negative. That tells me my ln Kp naught would decrease with temperature increase. Right. So you can imagine this picture will be very different if we have a endothermic reaction, meaning my delta H naught is a positive number, right? So the shape of that plot will be very different. But the way to derive that plot, it's going to be the same. And again, if you're watching the recording, the plot we're talking to is in chapter 6.2, 6.3. That's in the textbook. All right, and typically when we're talking about using our Van 't Hoff's equation for ideal gas reactions, so again, these are the equations we just write out here, right? So this delta H is something you can get from the thermodynamic table. And when we're calculating the change of my ln Kp, so in this case, if we do the integration on both ends, we got our ln Kp naught at T2 minus ln Kp naught at T1 equals to integration of my delta H over RT squared dt. All right, so this delta H should be a function of temperature. But when the temperature change is like very small, we will tell you that you can ignore the dependence of delta H with respect to temperature. And when I say small, I'm saying like delta T is within like 300 Kelvin. And this equation thus becomes the logarithm of Kp naught T2 over Kp naught T1 is about delta H naught over R, and you solve that integration, which is T1 minus T2. Note that this is only true when the temperature change is small. When temperature change is big, we need to tell you how does the enthalpy of the reaction change with respect to temperature. And how does temperature change of enthalpy with respect to temperature? Well, we just discussed that back here as we were talking about delta H naught as the integral of Cpm, which is the isobaric heat capacity, dt. Right. And that's isobaric heat capacity itself. So this is what we're talking about. So my delta H naught as a function of temperature is the integral of T1 to T2 delta Cp naught of the reaction of dt. Different versions of the Cp naught might exist. More often, it appears as like a polynomial that people get using polynomial regression from experimental observation. Depending on how accurate you want it to be, right? So by solving the integration here, you get delta H naught equals to like a big A plus BT plus CT squared plus DT third plus ET fourth. Right, so the whole point here is you can use our thermodynamic table to find a starting point of my equilibrium constant and my delta H. Right, but the delta H enthalpy itself might change with respect to temperature. So only using the thermodynamic table gives us the equilibrium constant at standard state and 298 Kelvin. But if the temperature change is like very vast, right, we're talking about equilibrium constant at 5,000 Kelvin, then there is a chance you need to use this equation to adjust for the temperature difference. Yes? Polynomial regression is basically this term here. It's like a plus b squared plus bx plus cx squared plus dx third.
Okay, so Cp is usually a polynomial.
Or basically, we'll give you that equation. That's the whole point. Okay. It's an equation. Cp is an equation of temperature that we will give you that equation if needed. Okay, any other questions before we move on to lecture 19? I know I'm behind. Okay. All right, let's see how far we go. Lecture 19. So that's where your handout is, and if you have one with you, we'll do one mock example question together. But before we do that, I want to go over the problem-solving steps to calculate ideal gas equilibrium or ideal gas equilibrium calculations. So the whole point of chapter 6.4 is application, right? We define our equilibrium constant, our Kp naught, and that's a product of your partial pressure of gases at equilibrium over the standard 1 bar, right? That's the equilibrium composition. Note that this little subscription EQ here tells you this is a composition at equilibrium. And the big K tells you that's calculated for equilibrium composition. Also, we know that how to calculate my delta G naught from our thermodynamic table, right? So that's a sum of your stoichiometric coefficients and then the standard Gibbs free energy of formation from the table. right? So one typical set of the problem we can ask you is say, hey, now I give you a chemical reaction of interest of an ideal gas reaction, right? Using the tabulated data, can you tell me, like, what is the composition of the equilibrium at equilibrium, right? If I give you like starting number of mole of some of the reactant, what's the final composition at equilibrium? So here are a few steps for a general ideal gas reaction. So first we calculate delta G naught of the reaction from the appendix table data. So that's the Gibbs free energy of the reaction. We use delta G naught equals to negative RT ln K to solve for equilibrium constant. Now this is for our reaction at 298 Kelvin. If the reaction is not at 298 Kelvin, we might need to adjust the Kp naught into the new equilibrium constant at a different temperature using the Van 't Hoff's equation. All right, so this one is like optional, may be applicable. And then express our equilibrium mole numbers in our reaction extension, right? So what does that mean? So we're looking at the number of mole of specific chemicals at equilibrium. That equals to number of mole of that chemical at initial state plus the change. So the change itself is the stoichiometric coefficient times the extent of reaction. Right, so this is, again, one of those equations. You want to know what that means. So the first one is the number of mole of I at equilibrium. Second one, number of mole of I initially. And this one is my stoichiometric coefficient times the extent of reaction or change. Right. And with this in hand, we can express our partial pressure, Pi, as a function of Ci, of the C equilibrium. So my Pi equals to the mole fraction times the total pressure. And then since we know our Kp naught, so this one is solved in step 2, right? And we can express the partial pressure of each my reactant and substrate in a function of C. We can solve this quadratic equation for the extent of reaction. And then at the end, we can calculate how does Ni change. Yeah.
What was the final variable in the equilibrium equation?
This one?
Yeah, in the equation above, yeah.
C, that's the extent of reaction. Again, remember we have, we'll see one example that becomes more straightforward. So the example here, again, if you have your note, we can do it together. Again, let's use our ammonia equation as an example, just to refresh your memory a little bit, right? You can have the initial number of mole of your N2, H2, and NH3. Let's say initially in the reaction mixture, we have 1 mole of N2, 2 mole of H2, and 0.5 mole of NH3, right? So when we set up this table, in this case, the change of the number of mole of each species for N2, well, this one is always equals to stoichiometric number times the extent of reaction C. So for N2, the change is negative C, so negative because of the stoichiometric coefficient is negative. This one is negative 3C for H2, and then 2C for NH3. Right, so the final number of mole, or the equilibrium number of mole, is thus becomes 1.0 minus C for N2, 2.0 minus 3C for H2, and 0.50 plus 2C for NH3. And taking it together, we can calculate the total number of mole. At equilibrium is the sum of all the species at equilibrium and add all these three together. And that becomes 3.5 minus 2C. All right, so that's a total number of mole. So since we're talking about ideal gas mixture, so we have one more step we can do to simplify this problem. So let's see if we have fixed pressure, so meaning the total pressure is fixed. So we know that my partial pressure equals to the mole fraction chi I times the total pressure P. Right. So what is my chi I? So my mole fraction equals to the Ni at equilibrium divided by N total at equilibrium times P. Just to simplify your system. All right. And a different kind of scenario, if we have fixed volume. So these two are different. It's like top or bottom. So you might have different conditions, right? So when pressure is fixed, we know that the partial pressure of each species equals to Ni equilibrium over N total equilibrium times total pressure. If the total volume is fixed, that tells us we have PV equals to nRT. So my PI equals to Ni times RT over V. All right, so in different conditions, we use different equations. So total pressure, you use the top one. Total fixed volume, we use the bottom one. And later on, we'll use these two equations for different conditions, whether it's constant pressure or constant volume. And at the end, later on, we'll define reaction quotient for ammonia synthesis. I'll give you the definition now, but we'll use it later on. So the definition of reaction quotient is now a random mixture, not necessarily at equilibrium. So that equals to the partial pressure of your products and reactants. So the way to use the reaction quotient is tells you like if my QP is smaller than KP, we have forward reaction. If my QP is larger than KP, we have backward reaction. We'll talk more about reaction quotient later on. All right, so this is a quick demonstration in some of the steps in the previous list. So now let's use these previous lists to solve a real problem. So here is a problem of interest, and we are gonna do it like step by step to solve this problem. And again, if you're watching the recording, you can refer to our annotated notes to get an idea about what we're talking about. All right, so what are the 6 steps? So going back to read the question together. So given that we have a system initially containing 0.3 moles of N2O4 and 0.5 moles of NO2, and we give you this equilibrium of the decomposition reaction. And the equilibrium is attended at 25 degrees Celsius to atm, and ask you to find out what is the equilibrium composition. Or the other way to put it is ask you to find out what is the number of mole of your N2O4 and the number of mole of NO2 at reaction equilibrium. So a few steps, right? So the first step is to calculate my delta G of the reaction from the tabulated data. And that's my stoichiometric coefficient times the delta G of formation of each species at certain temperature and that's from your thermodynamic table. Right, so in this case, I can give you the result to be 2 times 51.31 minus 97.89 equals to 4.73 kilojoule per mole. So these numbers are from appendix data. All right, so first use the table, find the delta G of the reaction. Second step, calculate my, what is my equilibrium constant, my Kp naught. So in this reaction, we're saying the equilibrium is attended at 25 degrees Celsius. So temperature is the same as the temperature of my appendix data. We can directly use my delta G naught equals to negative RT ln Kp naught. So we can solve, plug in our delta G and solve for our Kp naught to be 0.148. All right. What about the third one? And the third one, remember in that list, we're saying in the third one, you want to express the equilibrium number of mole of your species, right? So what are we looking at? So we're looking at the number of mole of my N2O4 at equilibrium equals to the number of mole of N2O4 initial. So this 0 represents initial plus the stoichiometric coefficient of N2O4 times the C of the reaction. Right, so we know the initial number of mole. The initial number of mole of my N2O4 is 0.3 mole. The stoichiometric coefficient is -1, and we can express that as a function of my extent of reaction. Right, the same applies for the product. So NO2 at equilibrium equals to the initial number of mole of NO2 plus stoichiometric coefficient of NO2 times extent of reaction. So initial number of mole is 0.5 mole and plus 2 C. So that's step number 3. All right. So step number 4, express our equilibrium partial pressure, PI, as a function of C. So what is our PI? So first we want to solve for the total number of mole at equilibrium. And that equals to the sum of these two values, which is 0.800 plus C. Right, so this is the number of mole of my N2O4 at equilibrium plus number of mole of NO2 at equilibrium. And then the partial pressure becomes quite straightforward. So in this reaction, we're telling you the equilibrium is reached at 2.00 atm. So we're looking at that constant pressure condition, right? So pressure is known, the total pressure is constant. So my PI equals to chi I times P. So the mole fraction times the total pressure here. So what is this number? So my partial pressure of N2O4 equals to the mole fraction of N2O4, and that is this one, 300 minus C over N total times the total pressure. Right, the same applies to my NO2. It's the number of mole of my NO2 divided by the total number of mole times the total pressure here. All right. This is number 4. And number 5, we know what my Kp naught is. We know what my partial pressures are. So we can solve for our extent of reaction. Right, so the way to set up our problem is my Kp naught equals to the partial pressure of NO2 over P naught to the stoichiometric coefficient of NO2 times the partial pressure of N2O4 divided by P naught over the stoichiometric coefficient of N2O4. Right, and do we know what these are? We have them expressed in C. So we can set up this equation to be 0.148 equals to, this one is 0.500 plus 2C divided by 0.800 plus C to its power, which is 2. Oh, and we want to take care of the total pressure over P naught. We need to take that over to the power of 2. And in here, we have our 0.33 minus C over 0.80 plus C, 2 times P over P naught minus 1. All right, so in here, our P equals to 2 APM, P naught equals to 1 bar. So we want to take care of that unit conversion in this step. All right. And now we have set up the calculation. It's obvious we can calculate for what the C is, or the extent of reaction. So, going back. So from here, we can solve for my C. So this one, since it's a quadratic equation, right, we have we have square here. We actually can get 2 results. So your C can either be negative 0.324 more or negative 0.176 more. But in here, you want to use one more common sense to think about this problem. Now, both of them are negative. One is negative 324, one is negative 176. But the problem here is we're looking at a backward reaction, right? So if we're looking at the backward reaction, we only have 0.5 more of NO2 available in our initial condition. So my C cannot be this top number. We don't have enough number of more of NO2 to afford this condition. So just one more thing to think about. And obviously, at the end of the day, you can come back and plug in the calculated extent of reaction into this expression to calculate the number of more of NO2 at equilibrium and number of more of N2O4 at equilibrium. So that's the last step to get numeric answer. Yes?
How do you know if it goes forward or backwards?
Well, it's a negative number, right? So when your C is negative, we're saying it's going backwards.
Okay.
We solved it to be a negative number, so it must be going backwards. Right, so this is one of those examples, like following the steps to solve for a seemingly complicated problem. If you look at the conditions we start from, right, we tell you what the initial number of more of different things, and using thermodynamics, you can predict what is the equilibrium composition of your reactant and product. So this is an example of the numeric answer. In our next lecture, we'll talk about how to solve it for a non-numeric answer, right? So in this case, like an isomerization of different species and express your mole fraction in equilibrium constant. And then in our next lecture, we will also talk about shifts in ideal gas reaction equilibria. And I'm afraid I don't have enough time to go to phase diagram, so we'll cut at chapter 6. So next lecture, we'll finish chapter 6. And well, unfortunately, I'll save phase diagram for your next physical chemistry class. Well, I'm not teaching it, so I don't know, but I might not have time to go to phase diagram. So chapter 6 is going to be our coverage for this entire quarter. All right, and stay for any questions you may have.